So African astronomical observatory, it is a huge letter. It is so many of you coming here in a Monday evening. So it's really appreciated. What? It's really appreciated to see so many of you here tonight. So thanks indeed for coming. So what's going to happen here tonight? In a moment, we will get a presentation by Jim Adams and Jim Green. And then, of course, after that, we will have an opportunity to ask them a few questions about the presentation. And then after that, you have to make up your mind. If you are interested in the history of this observatory, please do come and join me in the library afterwards, where I will be telling you what has been happening here for the last 200 years or so. And I can assure you, the history of this observatory is actually quite interesting. I can also assure you, I might be a bit biased. I'm working here after all. But it is interesting. So if you want, please come and join me in the library. If you're not so much into history, or you've had enough talking for the night, that's perfectly fine as well. Then you can skip that part and then go straight across the lawn and do some stargazing with small telescopes on the lawn, and do some stargazing with Cape Town's biggest telescope, the McLean telescope, and you can have a look at our museum as well, of course. But as you can imagine, with an event like this, there are certain rules and regulations. And you all know rule number 1. If you are the proud owner of anything known as smartphone, iPhone, Android, or even brick phone, switching it off or switching it to silent is actually a good idea. Rule number 2, while on site, please drive safely and slowly for 2 reasons. First, if you look around you, you may realize that there are visitors apart from you. And our visitors usually do mind if they are run over by a car. So we try to avoid that. But in addition to the visitors, you can see here, there might be other visitors as well, known as the Western leopard toad. And with no offense meant, the Western leopard toad might be the most stupid creature in the universe. Why? If I was a leopard toad that size and the car came approaching, I probably would hop away. But we can't rely on that. The rule of thumb is, if it's moving, it's probably not a leopard toad. So please don't run over them either, because from experience, they do look nicer if they are 3-dimensional. And rule number 3, I already mentioned that we can, of course, ask Jim and Jim about the presentation afterwards. You might have other questions about astronomy, of course, and if so, please don't hesitate. Grab any of the people wearing a fancy, stylish, greenish bib, or this nice, fancy SAAO gabel, and ask as much as you like. Terms and conditions do apply, though. If you're still asking at midnight, I'll send you home. But before then, that's one of the reasons we are here, so please do make use of the opportunity and ask whatever you always wanted to know about astronomy. I can guarantee you the answer will be for free, and if you're fortunate enough, it will even be correct. So there is not much to lose. Now, I'm notoriously bad at introducing speakers, so it is a real pleasure to hand over to Nick now to introduce the speakers properly. Thank you very much.
Okay, good evening, everyone. It's very nice to see a full house tonight. My name is Nick, by the way. I'm an astronomer here at the SAAO, so you can ask me a question as well. You might get a correct answer, I'm not sure. But I have the honor of introducing our two guests tonight. It's not many times that you can introduce two Jims from NASA. So the first is Jim Adams, former Deputy Chief Technologist at NASA. You might recognize his face because this is not his second or third time of visiting South Africa. It's his 23rd time that he's visited South Africa in the past 10 years, 24th time, doing what he loves, promoting space science and planetary science specifically. And our second guest is Jim Green, former chief scientist at NASA. And this is not his second or third or 24th. This is his first visit to South Africa. So please be nice because we want him to come again.
Thank you.
Yeah, and I can drone about all their achievements and all the NASA missions they've been involved in for longer than I've been alive. But I think you guys are here to listen to them talk about asteroids. So I'll hand over to which Jim?
Wow. Thank you, Nick. Oh my goodness, look at all these people. Thank you for coming out. It's just a real pleasure to be back here at the South African Astronomical Observatory. I have spoken here several times, but I want to tell you about a time when I didn't speak here. Steve Sherman, raise your hand, Steve. Yeah, had arranged for me to speak at a school for a school night, parents and kids. And the parents were so excited that they made all the kids sit in the back. Do you remember that? Yeah, they made all the kids sit in the back. And over the course of the evening, and there weren't enough chairs for the kids, so they had to sit on the floor. Over the course of the evening, the kids slowly slid on their bottoms forward up the aisles until all the kids were on the floor like you guys. And Steve's got some amazing pictures of me in a sea of kids, right? And that's what I love the most. I love when people get excited about science and learning new things and the subjects that we're going to talk about. So what Jim and I are going to do is we'll both start with a little introduction. You'll learn that I talk longer than Jim does about ourselves. And so I'll give you a little background on me, and then we'll talk a little bit about asteroids, and then Jim Green will talk a little bit about himself, and he will bring in the science, the planetary science of asteroids and how they're formed and where they come from, and what do we do about the ones that come really close. So let's begin. Let's push there we go. Okay, that's me when I was a better looking man. I was born in 1957. I have a BS in physics, an MS in electrical engineering. I spent 10 years at General Electric and 28 years at NASA. These are the jobs I've had: systems engineer, observatory manager, deputy project manager, and in green, deputy director of planetary science, the sweet spot in my career. In fact, there's a YouTube video, a TEDx talk that I give that's titled "The Coolest Job in the World." And that's exactly what this was. I was the deputy director of planetary science. That meant that the probe to Pluto, all the rovers on Mars, the Juno spacecraft at Jupiter, Messenger at Mercury, name it, Laddie at the moon. I got to help get built, launched, and on its way to capture the science that was necessary to expand human knowledge about this amazing solar system that we live in. The other really cool thing about that was I worked for this fella, Jim Green. And even though we had never met before I took the job, we really clicked. You know how it is when you make a friend and you guys are really accomplishing something special. And so that's what it was like for Jim and I. Sadly, what happens is once you start getting really successful, and Jim and I were extremely successful, we can talk a little bit about some of those missions later, the bosses start telling you what you need to do next. And so I was given an opportunity to become the Deputy Chief Technology Officer for NASA. And that was a cool job, but it wasn't planetary science. I was over at the White House. I was meeting with congressmen. Touring around the agency, looking at the various technologies we were developing and advising people on what was best for us to invest in so that when we went to certain destinations, we would have the technology that we needed. And then I retired in 2016. But I had come to have such a love of South Africa that even though I was retired, I kept coming back every 6 months, and nobody seemed to get tired of me. So, so here I am again. I'm back in South Africa, and it's just really a pleasure to be here and to show off South Africa to Jim Green. What we are doing here in South Africa this week is what we've termed the Space Tour South Africa 2025. Have any of you been to the website and seen that? Not very many people. Okay, so we start in Cape Town, and today, Stellenbosch, but tomorrow, where we'll be working with the SAAO and another organization called the African Astronomical Society, AFAS, to put on the very first African Lunar Symposium. Scientists from all over the continent are coming together to talk about the science that we can learn from the moon. Okay, now, who's still awake? Okay, all right. Just a little about me. I've had the opportunity to do a lot of things. This happens to be me on a launch console for a mission that was going to the moon with four-time astronaut General Charlie Bolden. And I have, this fellow's name is also Jim, really popular in the United States. I don't know why he's looking so serious because everything was going so well, but it was a fun job. Who has ever seen a rocket take off? Yeah. Wow. Would you like to see a video of one that we launched to send a spacecraft to the moon? All right, so here's the thing. We didn't make arrangements for house speakers, did we? It might work. Okay, well, let's give it a shot.
HDMI has a.
Let's.
Yeah.
Oops. No, huh? All right. 1, 0, liftoff. And most of what you're seeing here is steam. So what you'll see in about a minute is pieces of the spacecraft falling away. The reason that happens is those casings are spent. There's no more fuel left in them. And so we throw them away so we don't have to drag them all the way to orbit. They fall safely into the ocean, where they become inert and often found to be reefs where wildlife can thrive. So 45 seconds. Let's see, we'll wait until the solid rocket motors peel away. Oh, here we go. They look like big crayons.
Really big crayons. huh?
Really big crayons. No. And then the pieces fall away. And then the rocket continues on. Eventually, 3 more will separate. The first stage will burn out, the second stage will ignite and push Grail on towards the moon. We'll jettison the fairing, which protected it from the atmosphere. We don't need it anymore. And then the spacecraft will continue on to the moon. We'll take questions at the end, okay? Just remember, okay, try and remember what it was. All right. 90 seconds into the launch, the rocket weighs half of what it was when it was just sitting on the launch pad. That's how much power there was. When you saw me on the console, the roof of that building shook from the power of the launch. All right, well, sorry about not having the volume, we didn't test that. When we launch a rocket, it's extremely powerful. And so, because it's dangerous, you have to back up about 5 miles. That's as close as we'll let anybody get. So here's another mission that Jim and I put together, also went to the moon. Hey, guys. Also went to the moon. You can see it's getting ready to take off, and everybody's backed away 5 miles. Everybody got the message. So this spacecraft was on its way to the moon. And then when we developed the film, when we took the picture, we realized that this frog had not gotten the message to get away for 5 miles. The spacecraft made it to the moon, phoned home, and it was safe, but we never heard from the frog again. So up until about 1960, scientists thought that most craters that we found on the Earth were from volcanoes. But in fact, this fellow, Eugene Shoemaker, very famous scientist, was out at this crater in Arizona, and he found evidence that maybe it wasn't a volcano at all. And ultimately was able to prove that this crater was made by an impactor, an asteroid that came in through the atmosphere and hit the Earth and kicked up a lot of dust and made this amazing hole in the ground. There's a joke that thank goodness it landed here because it just missed that visitor center right there. But yeah, it was about 50 meters in size, and it released the energy of about 10 megatons from a nuclear explosion. And suddenly then scientists were finding craters all around the world. There are 2 really important ones here in South Africa. Just outside of Johannesburg is, I always pronounce it incorrectly, is Swang. Is that how you pronounce that? Swang crater. And in fact, there'll be scientists going to visit that later this week, or later next week, I should say. And then an enormous one that has been weathered so much that we only see pieces of it, but it's 300 kilometers across. And that's called the Redford Dome in South Africa. We're finding craters all the time on the Earth. Well, you don't see them as frequently as you do on the moon because the moon isn't weathering like the Earth is. You know, we have plate tectonics that are shifting the soils, and upheaval and weathering and there's, trees that grow and fall and they make soil, and so they're kind of hard to find, and sometimes they land in the ocean. But in fact, the Earth has been hit by a lot of asteroids as well. And so you can see sort of a map. Says so far. I believe this map, unless you updated this.
I didn't
No,
know.
this map was from 2013. So since then, there probably have been even more found. And you can see that the two in South Africa right there.
The latest new ones are in Greenland as the ice.
Those are in green.
Yeah, as the ice has melted, we have uncovered them.
It has a scientific effect, right? Gives us the opportunity
Yeah.
to see something we might not have seen if the ice hadn't pulled back. Kind of a serendipitous response. So there was this asteroid, and Jim's going to go into this in a little more detail, in 2013 called DA14. DA14 is a very large asteroid, and I think we have a picture of it. And we saw it coming, and we watched it really carefully, and we finally learned that it was not going to hit the Earth. But it was getting really close, and everybody worried about it. So we started telling people, you don't need to worry. But while we were watching DA14, the very same day, a much smaller asteroid came in over Chelyabinsk, Russia. And people were headed to work. And what happened was, nobody died, but as that asteroid came in through the atmosphere, there was a sonic boom, and it had glowed. It was a glowing ball in the morning sky. So people rushed to the windows to see what it was. And then the sonic boom came and fractured all the windows, and people got damaged by the flying blast. So about 1,000 people were hurt. And that was one of the times when we realized that, we really probably need to do something about this threat to humanity. And President Obama sent me here in 2013 to start to talk to South Africa about hosting a telescope that would help us find incoming asteroids, and not only protect South Africa, but also protect the rest of the people in the world. That's kind of like what we're talking about tonight. And that's how I met Nick all those years ago. Nick is now the principal investigator, co-investigator for the Atlas telescope up in Sutherland, and they make amazing discoveries all the time. Let's see, there's some more of the damage. Okay, so we were warning people about this asteroid, DA14. But this is the one that actually caused the damage. DA14 kind of sailed right by, close, but it didn't hit anything. Sailed, in fact, it came so close, it came between us and the moon. It came even closer. It came between the surface of the Earth and the geostationary belt where the satellites that broadcast television are. The good news is it didn't hit a TV satellite either. But how many of you have heard of 2014 YR4? No? You have.
Yeah, I am.
Nick has. Okay, 2014 YR4 is an asteroid that was discovered, I said 2014, didn't I? 2024 was discovered in December of last year. And when they started looking at it, they realized it's as big as a football stadium. And for a moment, we thought it was going to come close enough to Earth to impact it. And we're going to talk a little bit about what we did to understand that we were really safe all along. But you can see that these things get quite big. So this was about 19 meters across. I forget how big DA14 was. You remember, Jim?
I don't, but it's probably on the order of 50.
Yeah, it was about 50 meters across. And then, of course, the 2020 2024, YR4 is as large as this stadium. So, should we be worried about this? Let me tell you, you can sleep safe tonight. You don't, parents, you don't have to let your kids worry about this. This is a discovery rate chart. So as we look for asteroids, we find them in particular distributions. The red here are the really big ones. They're bigger than a kilometer across, and they could really do some serious damage, you know, like kill all the dinosaurs. Wait a second. All the dinosaurs are gone.
They've already done that.
It did that, right? But it could be a real threat to human beings. But one of the things you see here is that it's tapering off. The discovery rate is almost flat. Well, what that tells scientists is there probably aren't that many more to find, because we're constantly looking. Then there's the medium-sized ones, 140 meters or so. That's still climbing, but you can see there's just a little curve that's there. And then the smaller ones, the discovery rate is still growing. That's about 38,000 asteroids out there. And we estimate from these statistics that there's maybe about 60,000. So you can see that we still have 22,000 left to go. So we keep looking. All right. So 2024 YR4, it was in this orbit around the sun, very large elliptical orbit. You can see it crossed over the Earth's orbit, flew by Venus and Earth, and then was on its, oh, have I got this? No, yeah, here we go, 2024. And then crossed over the orbit of Mars, and then on out into space. And these little statues here, those are error bars. So when we first see an asteroid, we know it's approximately on this elliptical path, but we're really not sure exactly where it is on the elliptical path. So we keep looking. So the telescope in Sutherland keeps on looking. It's got brothers in Hawaii and Chile, as well as it's got colleagues at other observatories around the world. And we say, wow, this is looking like it could be a close call. Let's keep watching it. And let's see whether or not it's ultimately going to be a danger to humans. So if you were an astronomer, Nick, I think I got this right. This is what 2024 YR4 would look like. Little tiny speck, right? But the astronomers are smart. They know that asteroids move differently than stars and planets. And so this is what it looked like on subsequent observations. You can see it's jumping around a little bit, but it's on a path that's not normal for most solar system objects. So what would happen if it was going to hit the Earth? Well, when it was first found, it had a probability of hitting the Earth of, well, I've got the statistics on the next slide, but it was like about 1%. Well, that's kind of a big deal. You know, if this was the circle of the error of the path of the asteroid path would be right about here, or it might be up here, but it would be a little tiny thing. It would be smaller than my finger. And then it could go this way, it could go that way, it could go this way. But the Earth is like that. And my friends at Terra Planeta had Nick on when this was discovered. And one of the things Nick predicted was the probability of impact is going to go up. And that's exactly what happened. And then in subsequent observations, it went down, which he also predicted, because he's a really good scientist and knows exactly what's happening. Well, if it was going to hit the Earth, where would it hit? And this was the region that the scientists determined was at risk if that asteroid would come into Earth and into our atmosphere and impact the surface of the Earth. You can see that it's nowhere near South Africa, but if it were to hit on a landmass or even in the water, the effect of that, of the debris and the water vapor that would get picked up into the atmosphere would be a really serious thing, not just for people along this path, but all around the world. So we watched it. We kept on watching. We watched it a lot. And in January, it was predicted to be a 1.2% chance of hitting the Earth. In February, just like Nick predicted, it was 3.1%. But by the 13th of March of this year, it had dropped to 0.004. Well, why is that? It's because as we watched this, we better understood the error associated with the orbit of that asteroid. And as the error circle got smaller, the Earth was no longer inside it. So we knew that the Earth was safe, and we kept on watching. It's still a fantastic opportunity to understand about our solar system and how it was formed, because it's going to come right up close to the Earth, and we'll have an opportunity to observe it. So, where do they come from? What are we doing about it? Well,
Hi, Sue. I'm very delighted to be here. This is my first time in South Africa, although I've been in Africa before. I had a wonderful opportunity in the 80s to go to Kenya and participate in the launch in India. The Italian space there, which the Baltic launch pad. If you want to launch something that gets in the equatorial zone, that's a great place to be. And that was the San Marco project. I had a wonderful career for 42 years. And so for science fiction mottos, that's the answer. In that length of time, as a scientist, I walked through James Van Allen, first real space scientist, studied Van Allen. He was at the University of Iowa, which is in the middle of the United States. And I was based in Burlington. So my whole career, graduate, NASA scooped me up right away and the Martian space flight scientist. My spare time in Martian space flight, just astronauts in full suits and helping learn how to walk in space, do the water. My role was a safety diver, person suit safe. That was a blast. I also did a lot of science. Ended up with Goddard Space Flight.
training body to really understand the accretion process and what we will do. Out in the asteroid belt, planetesimals, right? Because as they're building blocks of planets, and then if they get big enough, and big enough seems to be around 500 kilometers in size, they get hot and they start melting on the inside, and now we're really going to form a planet. And so all the higher mass material like iron and aluminum will melt and come to the center and create a core. And that process is called differentiation, and it now becomes a planetesimal, the building block of a larger planet. Well, this is pretty much our view, and then we have Jupiter, which has got captured objects in two areas that are in its orbit. We call them Trojans. We actually have a mission, as you might have another mission that's going out to the Trojans and looking at what they really are. We think it's a mixture of a lot of these asteroids, but another group of debris that is well beyond Neptune, and Pluto is a part of that. It's not shown on this figure, and that is what we call the Kuiper Belt. And so we think a lot of Kuiper Belt objects and asteroids are trapped and create what we call the Trojans. Well, this is a pretty classical view of these objects, and how do we look for them is with ground-based facilities. And what we do when we look for near-Earth objects, we recognize that they're actually objects that were in the asteroid belt, and because of gravitational interactions, Jupiter's throwing them inward, in addition to many that are thrown outward. And so we then start a process of finding them, and as Jim showed you, we have found about 38 or 39,000 of them. We think there's at least 60,000 that are out there that we want to be able to find, some of which are, as Jim pointed out, pretty dangerous. They're prominent and larger. And many of them are much, much, much smaller than that we believe don't pose a hazard. But we want to be able to find them. And so we're still doing quite a bit of work in that area. So here's an Atlas telescope that, as Jim has already mentioned, Nick's very much involved in making this happen. It's a fabulous telescope here in South Africa, and it's covering an area that we just didn't have before, which is the Southern Hemisphere. But we also use telescopes in New Mexico, Arizona, and also Hawaii. So a lot of these ground-based telescopes are really important. Now, we actually want to look at shapes too. And we do that with radar. So I'm looking at the kids here, and I'm sure you kids recognize that when mom and dad get pulled over by a policeman, it's usually because they've used radar. Okay, you got that right. And how many times? Oh, that many? Okay, where the police officer is using radio waves to fire from the gun that they have in their hand, and it bounces off the car and comes back. And by doing multiple ones, they can determine distance and speed. And so consequently, we do the same thing. We do that with our Goldstone radar. We used to do that with the Arecibo radar in Puerto Rico, but that now is a facility that is out of commission. And here's one of the really nice ones that came by close to us. We had an opportunity to hit it with radar, and we discovered it's not one large object, it actually is two that have accreted together. So they also sometimes just saddle up and gravitationally begin to connect. And in fact, we can see sometimes in these wonderful images, some boulders that just kind of saddle up and sit there. Well, we now are going to change that initial picture I showed you that looks so nice, where the asteroids are just in that area, and really show you our discovery rate. And so every dot is a discovery,
you see the how the orbits of our planets are, where we're finding these. So here's where we are just 6 or 7 years ago in 2018, and then as we get to today, there's even more that we find. You can make out the asteroid belt, but as you see, there's also a continuum of near-Earth objects that swarm around the sun, orbit the sun just like the planets do, and of course, as they go around the sun, they'll cross our orbit. Not all of them do, but many of them do. Those are the ones we were worried about, or come close to us enough where our gravitation will pull them in, maybe on a subsequent orbit, maybe even the next orbit, they'll come around and impact the Earth. So to defend this planet, you need to be able to figure out where they are. So that's the fundamental thing that we're still working on, is finding all these objects. And we want to track them, and we want to watch their orbit, create a knowledge about their orbit. And we're finding out that over time, some of these orbits change from a variety of processes that we're also quite interested in understanding. So this is something we're going to have to do forever. Okay? Jupiter is still going to interact with them in the asteroid belt. There's millions of asteroids in the asteroid belt. Jupiter is still going to interact with them, and pieces of objects that have impact and created smaller pieces that end up in areas that Jupiter can push around will be pushed around, and they will come towards the sun and end up in orbits that may be dangerous for us. And so this is going to be a constant process from here on. And so when we talk about defending the planet, we're really talking about knowing as much about these objects as we possibly can, so we can figure out how to either change their orbits all at once or change their orbits gradually. And so those are the two approaches we're taking. Now, these are, of course, the smaller objects, the planetesimals, as I mentioned. Vesta is the second largest object in the asteroid belt, and it's about 500 kilometers in diameter, and it has a core of heavy material that already has started the differentiation process. Maybe this would have been the seed of the planet that would eventually have been created out in the asteroid belt. There's others that are like this, but indeed that's a fabulous asteroid. And we've been to it with the spacecraft called Dawn, because it goes to the asteroid belt, and this has looked the same for the last 4 billion years. Now, the ones I'm also going to talk about are in this little square. You can take a good look, kids, that are sitting in the front row. You might see a dot there, okay? And that is an asteroid, and it is huge. It's about 140 meters in length, and it is called Itokawa. And Itokawa was really looked at by a Japanese spacecraft called Hayabusa. Oh, it's actually even bigger than I thought, 540 meters. And you can see that this particular object has just accreted things. It's kind of come up and connected to it gravitationally. Sort of like a little vacuum cleaner that is attracting more and more objects out there. And the bigger that it gets, the more it's going to attract. That's a principle of gravity, of course. It also has a strange shape, kind of oblong. But if you take a good look, it almost looks like there's 2 major sections of it. One lobe here and another larger lobe here that have just kind of connected, and material then has started to accrete. And this is what we believe this is all about, is 2 very large asteroids that are on the order of 100 or 150 meters that are connected. And then all the little bitty pieces are moving on the surface as this goes around the sun and experiences all kinds of different radiation from the sun and sunlight, also the solar wind, and they roll downhill. because the center of mass has now changed. Each of these objects would have a center of mass inside them, but when they connect together, the center of mass is very different. And so all these smaller pieces form these nice little, what looks like smooth patches. But when we get down and look at them, they're anything but smooth. Now, we worked with the Japanese on this particular mission. Hayabusa 1 brought some samples back. And the samples they brought back told us about how the solar wind modifies the chemistry of the surface of these objects, so that when we take a spectrum of it, we don't really get the kind of information we like to get in terms of its composition. And that's because the solar wind has been impeded in the surface and changed its composition. The Japanese also launched another one, the second one, Hayabusa 2. And I went to this particular object, Ryugu, which is also quite large. It's even larger than Hayabusa, but it's very different in shape. It has some of the same characteristics. We don't really see any craters on it. I mean, it looks like there's some indentations, but that may have been some gentle pushing or impacting. But by and large, it's also an accreted set of material. We call these kind of asteroids rubble piles, because they've just collected material along the way. This one is a particularly important one based on what we believe is an important set of material. We call this a carbonaceous chondrite. It is just rich with carbon. And carbon is extremely important because it's one of those fundamental things that we have to have that goes into our plants and animals and life. So we're carbon-based beings on this earth, okay? So carbon is very important. Ryugu samples were taken. So let me show you. This also has some areas where it looks very nice, hardly anything going on. But in reality, and this is shot pretty much in real time, as the spacecraft is hovering over the surface, it's going to try to look for a location where it can come down. This is the smooth area, and it looks quite rubbly rather. And as we come down, and we're going to grab some material, some samples as we hit this. We hope we won't run into any big boulders. In fact, here's a big boulder. We just missed that. If we had hit that, we wouldn't have gotten the samples that we would have liked to have gotten. But you can see, just by touching it, pieces are flying all over the place. You go in the instrument, and close the door, and then we bring the material back and analyze it. And indeed, we find that this is very rich, and it has amino acids. All right, and it has many other things that will actually has a lot of frozen water also in this, and that of course we knew that was also an important material that's out in the asteroid belt is water. Okay. NASA also has a mission. This is another one of the missions that Jim and I were responsible for in planetary science. This is OSIRIS-REx, and this looks very much like Ryugu. It's only about half the size, so this is much more like, size-wise, 500 meters, much more like Itokawa. It has many of those features. It's a rubble pile. It has this ridge around what turns out to be the equator, and that's because all these things spin. And this is spinning. I think it has like a 6-hour rotation period. So as it spins, this material will move and get down into the equatorial zone. So we got down and we grabbed some samples, and then those samples were put in a capsule. And then as OSIRIS-REx left Bennu, flew back to Earth, it dropped the capsule off on Earth and on, then it went on its way to the next object, which it turns out it's going to go to Apophis. We'll have a good look at Apophis, which is another asteroid. It's a near-Earth object that will be coming close to the Earth in 2029. Now, what's really spectacular about this carbonaceous chondrite is its composition. So not only were we finding amino acids in a lot of them, we found all the nucleotide bases, not only for DNA, but for RNA. Okay? So this was quite exciting scientifically. It brings to mind how important these objects may have been in terms of bringing material to Earth early on that is needed for life. So indeed, the concept that we are talking about today are that near-Earth objects are bad, they hit us, they take out life. But in reality, it may be that near-Earth objects actually seeded life in this planet, or at least the building blocks, rather, of life on this planet, and got things started. And so you might think this is too much of a good thing because they keep bombarding us over time. But indeed, this was a little bit of a surprise. We knew that we'd find some amino acids and maybe a few of these more complex organic compounds, but all 5 of them was a real delight. This is the, by the way, this picture is the inside of the collection system. And so what we're looking at here are all the bits and pieces that when we touch down, they're sucked into this unit. So this indeed is the inside of that capsule that indeed we landed. Now, when these objects hit our atmosphere, which is really a great deterrent for them to be destroyed, they will make a sonic boom. At night, you can see them with a bright light. We call them shooting stars in many cases. And so we've been categorizing these for quite a while. So over a 30 or so year period, we have done a map based on what we know that hits our atmosphere. We call these fireballs or shooting stars. And then some idea of their energy, which gives us some idea of their size, okay? And then you look at the distribution, and they're all, it looks like it's pretty evenly distributed across the globe. Many of them will hit the atmosphere and go into the ocean. Others will hit the atmosphere over land. And the larger one up here turns out to be indeed shelly events. And that one was only between 17 and 19 meters. All right. So it wasn't really that big. So none of these are really the big ones, okay, that we're really worried about. These are going to continue to come down all the time. So to give you an idea of how much debris we end up getting per year, it's about 100 metric ton a year of meteoric material or asteroidal material that hits our atmosphere every year, right? And of course, all these will burn up in the atmosphere. It won't make it to the ground. You have to have something perhaps on the order of 40 to 50 meters in size before you'll actually have a solid object that will hit the ground, creating a crater. So these aren't the cratered ones, but indeed they're out there, and they will come if they cross our orbit and really affect life on this planet. So based on size, we can get an idea of how bad these would be if they hit the Earth. So there's many of the 10-meter size. We'll see these all the time, as I mentioned. They won't make it to the Earth. They'll have a sonic boom, fireball, of course, breakout windows. So this is on the order of what we see with Charlie Benz. And you start getting these, they're bigger, these are local devastations, meaning it will produce a crater, hit the ground. And you can see, you know, the number that we're talking about, even though we're looking for about 60 or 65,000 near-Earth objects, we're ignoring, you know, millions of smaller objects like this because they're not a threat. They'll burn up in the atmosphere in the 10-meter or so side. But as you see up in the 140-meter, these are real city killers. So if you're familiar with the Washington, D.C. area, it has a road that goes all the way around it. So this is Moscow. I could pick Moscow, but I'm talking about Washington, D.C., all right? There's a ring road, and we had a 140-meter NEO hit the center of Washington, D.C. It pretty well pulverized everything in this ring road. And then it would also have a variety of devastation into Maryland and Delaware and Virginia around. So, and then of course you get up to the 100, 1 kilometer and even larger. In fact, in that set of 1 kilometer and greater, the largest one is 33 kilometers. And so that is indeed an enormous NEO. Now, in reality, it sounds so small. Even a few tens of kilometers sounds small compared to how big the Earth is. So why are these so devastating? Well, they're so devastating for several reasons. One, they're moving incredibly fast, all right? And so as you can see, they hit the top of our atmosphere going a couple tens of kilometers per second, all right? And they're unstoppable. From here on down, they make it to the bottom and hit the ground. What will happen is material will be pulverized. Everything in the crater, it used to be dirt and rubble, and whether it's buildings or whatever, if it hits a populated area, will be pieces, will be total rubble. And that will have enough energy that it will be lofted into space. And when it gets lofted into space, it doesn't just come up and come down quickly. It actually will move through our atmosphere. This is our big problem. It will move through our atmosphere and will continue well into space. Now, the space station is up at around 450 kilometers. And these will easily, debris from these will easily reach the International Space Station, all right? So as this material moves up, the gravity of the Earth will start pulling the material back down, and so indeed it will start settling out and coming back down. In the meantime, the Earth is moving underneath that. So that material starts coming down in a region, and of course it's going to block the sunlight like crazy. And so you then end up with a structure in the high altitude atmosphere blocking the sun that will take, sometimes we estimate that, depending on how big the initial impact is, a decade or more before it actually filters through. This really affects our food chain. You can't grow plants in these areas. And so it becomes a global disaster. So even these small ones, 1 kilometer, or it would sound small, or can be quite devastating. So now that we know we're going to have to protect the Earth because there are those of size that can reach the ground, create the craters, create devastation globally, we have to come up with how we're going to mitigate these objects, because it's not a matter of if, it's going to only be a matter of when. And so consequently, we started a program in the area of planetary defense. In 2016, I organized within Planetary Science the Planetary Defense Coordination Office. And I assigned an individual to that office to run it, and that is the Planetary Defense Officer. And that individual is responsible for the entire program that NASA has put together and for developing a variety of communication strategies. That if we find something, there's a group that we notify, the president will be notified, analysis will be done internationally on its orbit. We have many groups around the world that help make observations that confirm it. And then we begin the process of notifying other nations, in particular those that would be affected. This impact corridor is calculated. All countries will be notified that there's a potential threat. And then over time, we start the process of, well, the corridor is getting smaller and smaller and smaller, and all of a sudden now the Earth is out of the way. That's what we hope to do. But if the corridor stays there and it's going to hit us, we then have to do something else, and that would be civil defense. So in the United States and in many countries in Europe have gone through the process of an exercise. We call this a tabletop exercise, where we talk about, okay, here comes a NEO, it's going to cross his areas, you're in the corridor, what is you as a country going to do? Are you going to notify the population? Are you going to move them out of the corridor? You know, what are the things that each of these countries do to save lives in this area? That's a process that's going on all the time. And as the group that has been in my organization, the Planetary Defense Office, will be here in a couple months. They'll be talking about these effects and talking about with other scientists and international leaders on processes and procedures that we feel are the right approaches to save lives on these. Now, I have to tell you, I don't want you to walk away being afraid, because in all this analysis, it looks like we're really in really wonderful shape for at least 50 years, probably more than 100 years. But after that, we're not quite so sure. We've got things we're worried about. We have things we have to look at. And that's a long time, all right? But if we don't start actively pursuing some ideas on planetary defense, we need to be ready in case we find one that we haven't seen before, that's on its way, for which that corridor stays on the Earth and will hit us. So this mission is called DART. And indeed, DART was launched in 2021. And the idea is, let's hit an asteroid that's at least 140 meters inside, you know, what we would call a devastation of a city, an area like a city, and see if we can move it. Now, this was discussed starting in early 2010, 2011, around in that time period, hotly debated on which one are we going to do. And it turns out it was a French scientist from the Canadian or the French Space Agency, CNES, came up with a wonderful idea. And that was, let's not hit one that is just orbiting the sun. Let's hit one that's orbiting a larger asteroid. And the rationale for that is if we hit an asteroid that's just a single asteroid orbiting the sun, it would be very difficult for us to predict exactly what it would do, because we've never done this before. And it would be horrible if we moved it into an orbit that actually put it on a trajectory against the Earth. Right. So why that would be really dumb. So let's hit a moon of an asteroid. Now, it turns out a lot of these asteroids, as you saw in that radar picture, had several. In that particular radar case, they came together. But asteroids are doubles and triples that orbit each other. And indeed, there was a really nice one. It's called Dimorphos, and that is a moon of Didymos. Didymos is about 160 meters, so it's right in that range. Dimorphos is about 780 or even 800 meters. So it is the anchor for the smaller one to orbit. So we figured if we hit the moon, we can easily watch the orbit change we'll get an idea how effective a kinetic impactor is to move an asteroid out of the way. So we ran the calculations and we figured it's going to be between 5 and 10 minutes. So in terms of changing its orbit. So in this particular case, Dimorphos orbits Didymos 11 hours, 55 minutes, and we were hoping for it to go 11 hours and 45 minutes. And of course, we in September, about 9 months later, hit this asteroid and indeed moved it. So here is the impact as observed from Earth, 11 hours, 55-minute orbit changed to 11 hours and 23 minutes. That's a 32-minute change, 3 times what we thought. Now, the really great news is that it made a significant difference. The bad news is we don't understand that. That always unnerves us scientists. We didn't get it right in the supercomputer. Then, what about it was wrong, right? So this is the process now that tells us we have a lot to learn about the densities, their compositions, and giving us an idea of how big an asteroid we actually can move. Now, of course, moving the asteroid puts it on a different orbit that over time, if it goes around the sun several times before it hits the Earth, or is supposed to hit the Earth, and we hit it early, perhaps 5 or 6 or more years before that impact would have happened, then that gradual change in orbit would be really noticeable and would clearly miss the Earth. And so this concept of kinetic impact is really, really important. Now, it turns out also, here it is right here, and here is the observations from Nick's Atlas, all right? And so here comes the impact, bam. This is also, as I mentioned, once again, ground-based telescope or Atlas telescope, and we were able to see that impact. Now, Didymos is going across, and it's carrying Dimorphos, okay? So we don't see Dimorphos in this, we just see the two of them together as reflected light. And so that cloud is really coming from that smaller body. All right, so end result is, we're on it. Planetary defense in this area is important. It can be thought of as an existential risk, although not an immediate one. And we have many other ideas that we're going to test over time. But I think we now have identified a potential problem. And indeed, the dinosaurs didn't have a space program, but we do. And we will continue to be vigilant to save the Earth if any of these things happen in the future. Thank you very much. Time for questions, yes?
Yeah, so thank you speakers again, and we will take some questions on.
All right. So one of the things I want to say is whenever I come here, anybody who asks a question gets an NASA sticker. So think of good questions, and we'll make sure that you get a sticker. I might enlist a helper or two. And then if you're a kid and you don't get a sticker, we have NASA tattoos and smaller NASA stickers. I'll put them on the table.
Oh, and they're removable.
Yeah, we don't want to see these stuck to like automobiles and the ceiling or your brother's mouth, whatever. Right? So please use them.
So who's got the mic? We're going to walk around with the mic wherever it is now.
We're going to do without.
Didn't we do that? We're not going to have a mic?
No.
All right, okay, so let's just answer the question. All right, go ahead. Yeah, that's fine. Let's do that. Mr. NASA, please stand up.
You want to sponsor what's the update?
Oh, it's really cold. It's freezing cold. It will be several hundred degrees below zero. Very cold. Good question. So when we go into space and, we do spacewalks, the astronauts, they're in these big puffy suits. But what you don't see is they're actually wearing underwear with tubes of water that run into all of their body. So that water is heated and is circulated and keeps them warm. Okay.
Yeah, how about this young lady on the aisle? She told me she was gonna have a question.
All right.
Yeah.
Yes, I would like to say, every chance of two asteroids colliding, and if there is a chance, what will happen?
They do all the time, in particular out in the asteroid belt. And when they do, then Jupiter just kind of helps keep them apart. Some pieces might come back together. And when they collide, they'll move in a particular area that Jupiter loves in terms of being a gravitational resonance that will take that object and then really fling it. So not only the impact pushes material around, Jupiter can grab certain pieces in certain areas and just throw it out of the solar system and throw it inward. This is why things that are going on in the asteroid belt are going to affect us in the future. Because the ones that come in are the ones that do that. Okay, I had asked this young man next.
How much of the weight of the rocket is fuel?
Oh, about 90%.
Yeah,
Rockets
almost all of them.
are pretty light when they're empty. And that, we do that by design because we really don't want to send useless weight to space. The thing that we really want to launch is not the rocket, but it's the satellite that's sitting on top of it. So we try and get as efficient as we possibly can when we design the rocket so that we can actually do what we need to do, which is send the spacecraft.
All right, young lady.
What do asteroids hit the International Space Station?
Oh, wow. Well, we want to prevent that. And so, the Earth is really pretty big, and we've been watching and making sure that no NEO hits the Earth. And space station is much smaller. Space station is about the size of that football field. Okay, so it's quite a large object. But we're not too worried about these kind of objects. We're actually more worried about little debris that humans make from satellites that go up into space and leave those satellites in space when they're no longer working. All that space debris has an opportunity to hit the International Space Station. But we stay on top of that. We look for those things too. To keep our astronauts safe, and they are notified every once in a while that they need to shelter in. So there are places in the International Space Station they go to shelter, while either we move the station during that time period, or we let that object, a derelict spacecraft, go by and be safe.
All right, let's let an adult ask a question.
Okay.
A grown-up. What would you like to ask?
In terms of these spacecraft that you use to crash into an asteroid, in terms of the size relative to the size of an asteroid, how big are these objects, these spacecraft actually be?
Relatively small compared to the asteroid. But the reason we can make a big change is that asteroid is moving very fast. So when we get in its path, the momentum of the asteroid and the opposite momentum, which is smaller, of the spacecraft comes together and has a big impact on the motion of the asteroid.
Jim actually gave away one of our secrets, and that is, it looks phenomenal. And you got an object you're moving, and you have another spacecraft that hits it. All we worry about is just getting in its path and letting it hit. Okay, and we've done that in a way that enabled that the impact and really move that asteroid significantly.
I see some hands.
Oh, way in the back. Yeah, that's right. All right, over here. All right, this gentleman right here behind the red hatted person.
So if the Earth is still here, like 3,000 years now, nothing can fit, what would the sky look like? Like, how different would it be from what we see right now? Like, is there a possibility of having two moons in the future?
Oh, good question, but that timescale is way too short,
Okay, what about 10,000?
still too short. Still too short. We won't have two moons. There's no chance that we're really gonna capture something anywhere near the size of our own moon. And in fact, our moon is not captured. It actually was made early on in the formation of the solar system. When two objects, the proto-Earth and an object about the size of Mars, hit each other, this is 4.5 billion years ago, and then it ended up with the moon and the Earth. That object was called Theia, and what remains then is the Earth and the moon. And the moon was really close to us, and over time, the moon gradually moved away from the Earth. We'll continue to move away.
Could I suggest that we take two more questions? I know you're all itching to ask questions. The two gyms are kind of, walk slowly and you can come up to them and ask them questions, because some of you are quite excited about checking out what's up there in the big telescope. Who was thinking about going to do that? It's not a small telescope, it's the big one. And I'm sure you're dying to know not what the moon looks like, but maybe what are the kinds of things we could see tonight?
Besides the moon. Planets,
The Rhine Nebula. I'll have to do that. So we'll take two more. I see a question right over here. Which one? Oh, that lady. Okay, we'll do one over there, and then we'll take one over here. All right.
All right, young lady.
It's the spacecraft.
Yeah,
Oh.
debris hits the spacecraft.
You know, all kinds of things happen compared, depending upon how fast the debris is moving, what the material is on the spacecraft that it hits. Did you know that the New Horizons probe that we flew to Pluto had designed into it a layer of Kevlar? What do we use Kevlar in? Does anybody know? Bulletproof vests. We put a bulletproof vest on the probe because we didn't know how much debris there was going to be that the New Horizons probe would run into when it got to Pluto. Sometimes when we go through a gentle shower like the Leonids, the spacecraft receives these impacts from the dust and the debris, but it doesn't hurt the spacecraft. What it actually does is makes a little ping, a little radio frequency, and some of our radios can pick that up. And that gives us an idea of how much mass hit the spacecraft, and it gives us a lot of science data as a result. So there are some instruments on board spacecraft that are intentionally designed to run into things so that we can understand the debris in and around our solar system.
And we had one question here.
So has NASA ever had the idea of extracting raw material or natural resources from distant asteroids?
Yeah. We know that there's all kinds of material that are in these asteroids that are important. Some of the most important things are platinum group metals. So our phone is full of platinum group metals. They're great because they conduct electricity and they don't rust. So they're highly valuable. And we mine them here on Earth. And we mine them out of the crust of the Earth. And what they really are, before they got embedded in the crust of the Earth, is they were cores of planetesimals that hit the Earth and left those metals on the surface. Okay, so we're really mining the cores of asteroids that have been differentiated to get the platinum group metals out. And whatever has hit us has also hit the moon. And we know there's quite a bit of platinum group metals and irons and things on the moon. And so our first approach would be to go to the moon and mine some things at the moon before we'll run down an asteroid. But But they are also important resources, and I'm sure way in the future that will be done to help further the society, along with the Martian Society and the Human Society.
So I think Nick wants to wrap things up.
Thank you very much.
And what we're gonna do, since you've been such a great audience and listened to us drone on and on, I'm gonna leave all these stickers behind. So if you didn't get one,
Take one.
come on up front and take one. NASA really loves your support. And one of the things I should point out is the role that South Africa is playing in protecting the planet. Not only is the, but the cameras for the DART mission were made in Stellenbosch. So that video that showed was by the Atlas telescope, but the cameras that guided it, the DART into the moon, they were made right here in South Africa. In addition, as Jim mentioned, later this year in May, the world will meet in South Africa to come together and discuss what might happen and how might the world respond if one of these objects, near-Earth objects, were determined to actually become a threat to human populations. So you can be proud to be in South Africa helping the world. Thank you very much.
Yes, thank you.
So, as I mentioned before the presentation, if you are interested in history, join me in